In most countries, freight railways cross states. In Australia, they cross entire climates, from the tropical humidity of Queensland to the searing desert heat of the Nullarbor Plain, from steep coastal grades to thousand-mile stretches of dead straight track where the horizon never seems to move. And through all of it, one locomotive was specifically engineered to handle every single challenge this vast continent could throw at it. This is the story of the NR class, Australia's heavy haul success. A locomotive that didn't just move freight across distances that would span multiple European countries. It fundamentally changed how Australian rail freight operated, survived conditions that would cripple most diesel electrics, and became so reliable that it was trusted to haul both multi-thousand-ton steel trains and Australia's most prestigious passenger services. The NR class represents something rare in railway engineering, a design that got it right the first time, built specifically for one nation's unique demands, and proved so successful that decades later, it remains the backbone of transcontinental freight operations. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. By the early 1990s, Australian National Railways faced a crisis that threatened the viability of long-distance rail freight across the continent. The problem wasn't just one failing locomotive, class, or a single operational bottleneck. It was systemic, expensive, and getting worse every year. Australian National's locomotive fleet had become a maintenance nightmare. The CL class, DL class, 81 class, and various GM units were aging rapidly, and reliability had deteriorated to the point where canceled services and delayed freight were becoming routine rather than exceptional. When a locomotive breaks down 800 kilometers from the nearest workshop in 43-degree heat, the cost isn't just a repair bill. It's spoiled cargo, missed connections, customer penalties, and freight business permanently lost to road transport. And road transport was winning. Australia's highway network had expanded dramatically through the 1980s, and road trains, those massive multi-trailer trucks unique to Australia, were proving they could deliver freight faster and more reliably than the struggling rail network. The economics were brutal. Every percentage point of market share lost to trucks meant less revenue to maintain an already struggling railway infrastructure. But the problems went deeper than aging equipment. Australia's rail network had inherited a chaotic legacy from its colonial past. 3 different track gauges across the country: broad gauge in Victoria and South Australia, standard gauge for the interstate main lines, and narrow gauge in Queensland and Western Australia. This meant locomotive fleets had to be gauge-specific maintenance facilities duplicated across states, spare parts, inventories multiplied, and crew training fragmented. The cost inefficiency was staggering. Australian National needed a solution that addressed all of these problems simultaneously. Higher horsepower to reduce the number of locomotives per train. Dramatically improve fuel efficiency to compete with road transport on operating costs. Long-distance reliability that could handle 3,000-kilometer runs without major servicing. And crucially, standardization. One locomotive design, one training program, one spare parts inventory, one maintenance protocol. A national standard locomotive that could operate from Melbourne to Perth without the wheels falling off. Quite literally, the tender specifications were demanding because they had to be. The successful locomotive would need to survive sustained operation in 45-degree desert heat. It would need to handle extreme temperature cycling, from freezing desert nights to midday conditions hot enough to buckle poorly maintained track. It would need air filtration systems robust enough to keep operating through dust storms that turn day into night. It would need to idle for extended periods in remote locations without overheating or draining batteries. And it would need to do all of this while being economical enough to justify the capital investment. The contract went to Goninan, an Australian rail manufacturing company working with General Electric technology. They wouldn't be building an American locomotive with a few modifications. They would be designing something fundamentally adapted for Australian conditions, even if it used proven GE components as its foundation. When Goninan's engineers sat down to design what would become the NR class, they weren't working from a standard locomotive template. Every major system had to be reconsidered through the lens of Australia's extreme environment and operational distances. Start with the most fundamental challenge: heat. A diesel-electric locomotive is essentially a mobile power plant, generating enormous amounts of waste heat that must be dissipated continuously. In North America or Europe, ambient temperatures rarely exceed 35 degrees Celsius, and when they do, it's newsworthy. In the Australian interior, 45-degree days are routine during summer, and track temperatures can exceed 60 degrees. This isn't a minor engineering adjustment. It requires fundamentally different cooling architecture. The NR-class radiator system is oversized compared to equivalent horsepower American locomotives. Twin radiator banks with increased core area, oversized cooling fans, and heat exchangers specifically calibrated for sustained high-temperature operation. The cooling system alone adds several tons to the locomotive's weight, but without it, the engine and traction motors would overheat and fail within hours of leaving a coastal city. Then, there's dust. Australian red dust isn't like the grit you find on European railways. It's fine, pervasive, and abrasive. It infiltrates every gap, clogs every filter, and grinds down every moving part it reaches. The NR-class air filtration system is consequently massive, with multiple filtration stages and larger capacity filters than standard GE locomotives. The intake design includes pre-separators that remove the heaviest particles before air even reaches the primary filters. In American service, these filters might be serviced every few weeks. On the Nullarbor, they require inspection after every round trip. Distance creates its own engineering requirements. When your maintenance facilities are 1,500 kilometers apart, you can't design a locomotive that needs frequent workshop attention. The NR class uses modular construction, with major components grouped into removable pods that can be swapped relatively quickly at remote depots. Traction motor assemblies, cooling system components, and major electrical cabinets are designed for replacement rather than in situ repair. This reduces the time a failed locomotive spends at an outstation and gets it moving toward a proper workshop faster. Weight distribution became another Australia-specific consideration. The NR class carries 132 tons distributed across 6 axles, giving it 22 tons of axle loading. This weight distribution was carefully calculated for Australian track conditions, which vary dramatically. Coastal main lines have well-maintained heavy rail. Interior routes often feature lighter rail and less maintenance. The weight per axle needed to be high enough for traction on long grades, but not so high that it would damage lighter track sections or accelerate rail wear excessively. Noise standards in Australia were stricter than what GE was accustomed to in the American market. The NR class cab features enhanced sound insulation, a floating floor design that decouples crew space from structural vibration, and acoustic dampening around the engine compartment. This wasn't purely regulatory compliance. Crew comfort matters when your shifts involve 12 hours or more on transcontinental runs. A quieter cab reduces fatigue, improves alertness, and ultimately enhances safety. Even the fuel system reflects Australia-specific thinking. The NR class has extended fuel capacity for its horsepower rating, with tankage designed for very long intervals between refueling stops. The fuel system includes additional filtration to handle fuel quality variations between remote outback stations and major city terminals. Fuel contamination that might be merely inconvenient in a densely served network becomes critical when the next fuel point is 800 kilometers away. The GE 7FDL12 engine at the heart of the NR class might be an American design, but the Australian version received significant tuning modifications. The turbocharger calibration differs from US specifications, optimized for sustained medium-speed running rather than short-haul heavy. Acceleration. The fuel injection mapping prioritizes steady-state efficiency over peak power output. The oil system has increased sump capacity to extend service intervals. These aren't dramatic redesigns, but they represent careful adaptation to Australian operational profiles, where locomotives spend days cruising at constant speed, rather than hours switching in yards. The NR class generates 4,000 horsepower, which in the early 1990s positioned it as a genuinely high horsepower locomotive for Australian service. But raw power numbers tell you almost nothing about what makes a locomotive successful in heavy haul service. The engineering is in how that power gets delivered to the rails, how the systems stay reliable under stress, and how everything works together across thousands of operating hours between major services. The GE 7FDL12 engine drives an AR-15 alternator, which in turn supplies DC power to 6 GE752AH traction motors. This might sound like standard diesel-electric architecture, and fundamentally it is, but the Australian implementation includes specific adaptations for long-distance heavy haul. The engine's governor curves were programmed for Australian rail profiles, where sustained 110 km/h running might continue for 6 or 8 hours without significant throttle changes. American freight locomotives rarely see this kind of extended constant speed operation. They're designed for shorter distances with more speed variation, more braking, more throttle cycling. The NR's engine management system prioritizes thermal stability and fuel efficiency in the steady-state regime. The traction motors themselves feature enhanced ventilation, absolutely critical for Australian conditions. When you're hauling 2,000 tons up a grade in 40-degree ambient temperature, those motors generate tremendous heat. Insufficient cooling means thermal cutouts, reduced power, and potentially damaged windings. The NR-class motor cooling system moves larger volumes of air through the motor casings, with filtration specifically designed to keep out that omnipresent red dust while maintaining sufficient airflow. The bogies represent one of the most important aspects of the NR's success in Australian service. They're a development of GE's high-adhesion truck design, but with modifications for Australian track conditions and operating speeds. The tri-mount configuration, where 3 points support the bogie frame, provides excellent weight distribution across the 6 axles while maintaining flexibility for curve negotiation. Australian main lines include curves that would be considered tight for a high-speed freight route, particularly in coastal mountain ranges. The NR needed to handle these without excessive flange wear or rail damage while still performing well on the long, straight desert sections. The suspension system uses a combination of coil springs and hydraulic damping, calibrated for the rough ride quality of interior tracks. Australian track maintenance standards in the 1990s were variable, especially on routes with lower traffic density. The NR's suspension had to absorb significant track irregularities without transmitting excessive shock loads to the frame or losing rail contact. At the same time, it needed to remain stable at the NR's 115 km/h maximum speed, which is quite fast for a heavy freight locomotive. Wheel slip control in the NR class uses microprocessor-based systems that were relatively advanced for the early 1990s. The system continuously monitors individual wheel speeds and modulates traction motor current to prevent sustained wheel slip. But the programming had to account for Australian rail conditions. Australian rail metallurgy differs somewhat from North American practice, and track contamination patterns, whether from dust, salt, or organic matter, create different adhesion characteristics. The wheel slip system needed tuning to avoid being overly sensitive, which would cost tractive effort, while still catching slip events before they became damaging wheel burns. The sanding system deserves mention because it reflects practical Australian experience. Desert conditions mean dry rail most of the time, but when it does rain in the interior, it often creates a slippery film before enough water accumulates to wash surfaces clean. The NR's sanding system has larger sand capacity than comparable-length American locomotives, and is designed to function reliably with the very dry sand available in Australian deserts, which doesn't always flow as consistently as moisture-conditioned sand used elsewhere. Electronics packaging throughout the NR class reflects Australian temperature and the dust realities. Control cabinets use positive pressure ventilation to keep dust out while maintaining component cooling. Circuit boards and connectors received conformal coating to resist moisture during coastal operation and corrosion from salt air in areas near the ocean. Diagnostic systems were simplified compared to contemporary American locomotives because Australian maintenance facilities, especially remote ones, had limited access to specialized GE diagnostic equipment. The NR needed to provide useful fault information through relatively basic display systems that didn't require factory-level diagnostic tools. The cab environment includes features specifically requested by Australian crews. Large windshields provide excellent visibility for wildlife spotting, critical on routes where hitting a camel, kangaroo, or cattle can cause serious damage. Sunscreen roller blinds help manage the intense glare common in the interior. The air conditioning system has substantial capacity, essential for crew survival during summer transcontinental runs. Seating was designed for very long shifts, with better lumbar support than typical North American locomotive seats. These might seem like minor comfort features, but when you're operating a locomotive for 12 or 14 hours straight, comfort directly affects alertness and safety. When the first NR-class locomotives entered service in 1996, Australian National finally had the tool they needed to rationalize their diesel fleet. But what actually changed in day-to-day operations reveals far more about the NR's success than any technical specification. The most immediate impact was fleet simplification. Routes that previously required multiple locomotive types, each with different maintenance requirements, training needs, and spare parts inventories, could now be handled by NR-class units. A Melbourne to Perth freight that might have previously used CL-class units to Adelaide, then required a locomotive change to different power for the transcontinental leg, could now run with NR units for the entire 3,400-kilometer journey. This eliminated locomotive change time, reduced crew complexity, and meant the same maintenance crews could service units throughout the route. Fuel consumption improvements were substantial and directly visible in operating costs. The NR class achieved roughly 15 to 20% better fuel efficiency per ton kilometer than the older units it replaced. This wasn't due to any revolutionary technology, but rather the cumulative effect of better engine tuning, improved aerodynamics, reduced parasitic losses, and microprocessor controls that optimized engine loading. On transcontinental runs covering thousands of kilometers, this efficiency gain translated to tens of thousands of dollars saved annually per locomotive. Reliability metrics told an impressive story. In its first years of service, the NR class achieved availability rates above 90%, exceptional for a first-generation design. The locomotives routinely exceeded their scheduled maintenance intervals without component failures. Most significantly, they withstood the dust storms and temperature extremes that had plagued earlier classes. Stories circulated among maintenance crews about NR units returning from Nullarbor crossings with thick dust coating every external surface, yet all systems functioning normally because the air filtration had done its job. The NR's performance on grades proved particularly valuable. Australian transcontinental routes include significant grade sections, particularly in the Flinders Ranges and crossing the Nullarbor's edges. The combination of high continuous power output and excellent adhesion meant that NR-class locomotives could maintain schedule speeds on these grades with tonnage that would have required additional units from older classes. Reducing the number of locomotives per train saves fuel, reduces crew requirements, and decreases the probability of an en route failure. Intermodal freight operations benefited enormously from the NR class. Intermodal containers demand relatively fast, consistent transit times to compete with road transport. The NR's ability to sustain 110 kilometers per hour with intermodal trains meant Sydney-Perth transit times dropped to under 60 hours for priority freight. Consistent performance meant predictable schedules, which meant customers could rely on rail for time-sensitive cargo. This reliability helped recapture freight business that had been lost to trucks during the unreliable years of the early 1990s. Perhaps most unexpectedly, the NR class found regular use in passenger service. Both the legendary Indian Pacific and the GAN, Australia's premier transcontinental passenger trains, frequently operated with NR-class locomotives. This dual-use capability was unusual. Most heavy freight locomotives are too rough riding or noisy for passenger service. The NR's ride quality, low cab noise, and smooth throttle response made it acceptable for passenger operations, which saved Australian National from maintaining separate passenger locomotive fleets for these services. Passengers didn't particularly care what was pulling their sleeper car across the Nullarbor, but railway accountants certainly appreciated the fleet rationalization. Train handling characteristics earned praise from drivers. The NR's throttle response is progressive and predictable, without the abrupt power surges that can break couplers or damage lading. The dynamic braking system provides excellent control on descending grades, smoothly converting kinetic energy back to electrical energy, dissipated through resistor grids. Drivers reported that the NR felt solid and stable, even with heavy tonnage and gusty crosswinds common on exposed desert sections. Operationally, the NR class enabled longer trains with fewer locomotives. A steel train from Whyalla to Port Kembla hauling several thousand tons of raw steel products, might require 3 NR-class units where previous operations would have needed 4 or 5 older locomotives. This doesn't just save the operating cost of the additional units, it reduces train length, making it easier to fit trains into passing sidings on single-track routes. Shorter trains also reduce the risk of coupler failures and broken trains, both significant sources of delay. The NR's performance in extreme heat deserves emphasis because this is where many locomotive designs fail in Australia. During summer, interior temperatures regularly exceed 45 degrees Celsius. Track temperatures can reach 60 degrees or higher. Under these conditions, many locomotives experience coolant system failures, traction motor overheating, and electrical component failures. The NR class, with its oversized cooling system and robust thermal management, continued operating when older units would have been sitting dead on the main line waiting for rescue. This reliability in extreme conditions was perhaps the single most operationally valuable characteristic of the design. The NR class became more than just a successful locomotive design. It became a visual icon of Australian rail freight, with livery variations that reflected the complex corporate changes, sweeping Australian railways through the 1990s and 2000s. The original Australian national red and white livery established the NR's appearance, a bold red body with white window bands and gray trucks. This scheme was clean, distinctive, and highly visible in the desert landscape. But as Australian National fragmented and privatized, the NR fleet dispersed across multiple operators, each applying their own corporate identity. National Rail Corporation, created in 1992 to take over interstate freight operations, applied a blue and gold livery that became closely associated with the NR class. This sophisticated color scheme, with its flowing diagonal stripes, transformed the industrial locomotive into something approaching elegant. Railway photographers loved it because the colors photographed beautifully against red desert earth and blue sky. Pacific National, which emerged as the dominant freight operator after further railway consolidation, applied their blue and yellow scheme to much of the NR fleet. This simpler livery prioritized corporate branding visibility over aesthetic refinement, but it became the most commonly seen NR appearance through the 2000s and 2010s. Specialty liveries gave individual units unique character. NR30, painted in an indigenous-themed livery and named Kimba, featured Aboriginal artwork and served as a cultural ambassador for reconciliation efforts. The Steel Link livery, applied to units dedicated to steel traffic, used bold red and gray colors reflecting the industrial nature of the cargo. Trailer rail units, used for intermodal services, carried a distinctive orange and white scheme. The Indian Pacific and the GAN passenger services each had dedicated NR-class units and matching liveries. The Indian Pacific units wore deep purple and cream, echoing the passenger car colors. GAN units featured red and silver, creating visual continuity when the locomotive was coupled to the matching passenger consist. Seeing a freight-designed locomotive in passenger livery initially seemed odd, but it reinforced how versatile and successful the NR design had proven. Special commemorative units appeared periodically. NR25, painted in a Trans-Australia Heritage livery, recalling the railroad's historical identity, became a favorite among enthusiasts. Limited-run anniversary schemes and charity-themed liveries added variety to the fleet. The NR class also underwent technical variants as operational experience accumulated. Some units received upgraded cooling packages with even larger radiator cores, intended for the most demanding summer services. Bogie overhauls introduced improved suspension components and bearing systems. Electronic control systems received software updates and, in some cases, upgraded processors. These weren't dramatic enough to create distinct subclasses, but they reflected continuous improvement based on real-world performance data. By the 2010s, as the original NR fleet approached 2 decades in service, major rebuild programs began. These weren't just routine overhauls. They involved replacing worn components with improved versions, updating electronics with modern equivalents, and extending the design life into the 2030s. The economics of these rebuilds demonstrated the fundamental soundness of the original design. Rather than replacing the NR fleet with new locomotives, operators chose to invest in extending NR service life, confident that the basic platform remained competitive. Culturally, the NR class achieved a status unusual for freight locomotives. It appeared in documentaries about Australian railways, featured on the calendar pages and magazine covers, and became one of the most photographed locomotives in the Southern Hemisphere. Railway enthusiasts recognized NRs by their distinctive tall profile and sound. The GE7FDL engine has a characteristic exhaust note, deeper and more resonant than the EMD two-stroke engines in competing Australian locomotives. Trackside, you could often identify an approaching NR by sound before it came into view. The NR class also became shorthand for Australian railway competence and adaptation. Here was a locomotive designed specifically for Australian conditions, using proven technology thoughtfully applied rather than exotic innovation. It worked reliably in an environment that destroyed less carefully engineered machines. It proved economical enough to justify its capital cost, and it lasted, still hauling freight decades after entering service when many contemporary locomotive designs had already been retired or relegated to secondary duties. More than 25 years after the first NR-class units entered service, they remain central to Australian transcontinental freight operations. This longevity itself tells the success story. Locomotive designs that fail operationally or economically get retired quickly. Designs with fundamental flaws get rebuilt beyond recognition or withdrawn. The NR class has done neither. It continues operating in essentially its original configuration because the original configuration works. The NR represented something increasingly rare in locomotive engineering, a design optimized for specific operational requirements rather than generic global markets. Modern locomotive manufacturing emphasizes standardization and commonality across international markets to achieve economies of scale. This approach produces competent machines, but rarely produces locomotives perfectly suited to any particular environment. The NR class went the opposite direction. It was uncompromisingly Australian in its design priorities, and that specificity proved to be a strength rather than a limitation. The success of the NR class validated Australian rail engineering capabilities during a period when Australian railways were struggling with relevance and financial viability. Here was proof that Australian engineers, working with Australian operators and manufacturers, could produce world-class railway equipment specifically adapted to Australian conditions. This wasn't about national pride or protectionism. It was about the practical reality that sometimes local expertise and local adaptation produces better results than importing foreign designs unchanged. For modern heavy haul operations, the NR class demonstrated principles that remain relevant. Design for your actual operating environment, not theoretical specifications. Prioritize reliability and maintainability, not just peak performance. Make systems robust enough to handle your worst conditions, not just your average conditions. Accept that specialization sometimes produces better results than standardization. These lessons apply far beyond Australian railways. The NR class also illustrated how locomotive service life can extend well beyond original expectations when the fundamental design is sound. With appropriate maintenance and periodic upgrades, a well-designed diesel-electric can operate effectively for 40 years or more. This economic reality shapes modern locomotive acquisition strategies. The capital cost of new locomotives is so high that extending existing fleet service life often provides better return on investment than replacement, assuming the existing design remains operationally adequate. Today, as Australian railways consider future motive power needs, the NR class casts a long shadow. Any new locomotive design must match or exceed NR reliability, fuel efficiency, and operational flexibility. That's a high bar, and it explains why the NR fleet continues in service when you might expect newer designs to have displaced it. The newer alternatives haven't proven sufficiently superior to justify scrapping still functional NR units. The NR class became one of the great heavy-haul success stories of the modern diesel era, not through revolutionary technology or exotic innovation, but through careful engineering specifically adapted to difficult operating conditions. It moved a nation's freight across a continent for decades, reliably and economically. That's the definition of success in railway engineering: simple, rugged, efficient, and unmistakably Australian. That's the NR class legacy.